Hello everyone, I'm Kashish Patel, a master's student at CEPT University pursuing the program Construction Engineering and Management. My student code is PCM24166. I will be presenting my portfolio for Studio 2 Construction Project Execution Monitoring and Control for the project Corporate House located in Gift City. This presentation outlines key aspects of execution planning and monitoring tools and material and quality management techniques used in this project. This is a greenfield development project under the real estate sector designed as a high-tech office space for a software company. The site is located in the special economic zone of Gift City with a total site area of about 2,531 square meters and a built-up area of 23,640 square meters. The structure includes 3 basements, a ground floor, and 13 upper floors. The construction began in October 2023 and is scheduled to complete by May 2025, with an overall project cost of 144 crores and construction cost of 76 crores. Moving on to pour planning, all calculations are done for one floor slab cycle. Typical slab is divided into two pours, where pour 1 is post-tension slab of area 327 square meters and pour 2 is conventional slab of area 809 square meters. Starting with formwork planning, there are three types of formwork systems used: peri-handset alpha for columns, peri-alpha deck system for slab, and conventional formwork for beam bottoms. Couplock system is used for scaffoldings. We can see the section for column and lift wall formwork here. All the elements of formwork were calculated according to these plans. Tables here show the breakdown of formwork components for columns and lift walls. This slide continues with formwork planning for slabs and beams. We calculated required elements for the slab, including total components for slab, beam, and couplock system. Productivity calculations were done according to the table given. The graph shows pour-wise productivity of workers for shuttering of different elements. Two sets of formwork are used on site. Set repetition is done on alternate floors according to the slab cycle. The figure given shows the set repetition of formwork for typical floors. The total cost of formwork was derived using material and labor costs. Repetition was considered according to the life cycle of formwork elements to derive cost per repetition. Reinforcement is planned and estimated for horizontal and vertical elements pour-wise. Steel coefficients were calculated using dimensions of elements from structural drawings and steel quantity derived from the bar bending schedule. Steel quantity for all individual elements was calculated using coefficients as shown in the table given for steel in slab for pour 1. We can observe that coefficients for steel for elements of pour 1 are lesser than that of pour 2. This is because pour 1 is a PT slab and requires lesser quantity of reinforcement. Here, we have also shown total quantities of steel for pour 1 and pour 2 along with labor productivity of each element. Total reinforcement cost includes material and labor costs. Cost comparison for using manual labor versus tower crane for handling of reinforcement is also provided. This slide outlines our concrete cycle planning. The slab cycle duration for each floor was calculated with 8th floor used as a reference. Quantity of concrete for each pour was calculated according to the dimensions of elements using structural drawings. Coefficient of concrete is calculated as per the estimated quantities required per pour. Details like number of transit mixers, productivity, and cost for both labor and materials are also calculated. This allows us to streamline manpower allocation, equipment deployment, and inventory flow, ensuring timely execution. Material management was done using multiple analytical tools. Using ABC analysis, we found that reinforcement and RMC account for 99% of material cost, highlighting them as A-class materials for the project. This analysis can be used to set procurement priorities and ensure close control over these items based on their class. Next is HML analysis. Here, reinforcement, binding wire, and nails fall under high value items needing strict controls. Conversely, AAC blocks and RMC, being low value items, are managed with leaner oversight. Cost of items shall be considered for the same unit for HML analysis. Here, all costs are taken per kg for all 5 items. Thus, RMC falls under low value item category. We also use the classical EOQ model and EOQ model with a price break scenario. This helped to determine the most economical quantity of steel to order, balancing carrying and ordering costs. For EOQ model with a price break of rupees 2000 is considered. We can observe that the optimal order quantity is inversely proportional to the purchase price, which suggests that bulk purchasing at lower purchase price leads to cost efficiency. This slide shows how quality control tools like XPAR and R charts are used to monitor the 28-day compressive strength of M60 grade concrete. The table on the left includes key values like the average strength and average range. Based on these, control limits are calculated using standard factors. The XPAR chart shows that most sample strengths are within the control limits. Only 2 points exceed the upper limit, which we assume may be due to improper casting or testing. We can observe that all the values fall within the IS standard deviation. The R chart below shows that the variability across samples stays well within the control limits, indicating consistent mixing and testing. Histograms help visualize rolling margin limits, ensuring that material variability stays in check. IS limits for difference percentage in rolling margin of 12 mm to 16 mm diameter bars is plus or minus 5%. Using the histogram, we can derive that one sample was not within the IS limit. For 8 to 10 mm bars, the IS limit for difference in rolling margin is plus or minus 7%. We can observe that all samples fall within the standard limits. Ishikawa diagram was another tool we used to identify root cause for a non-conformity observed on site. A wooden batten was left in a beam joint during concreting, creating a gap and potential durability risk. Ishikawa diagram shows possible causes of the problem, with the root cause being no inspection, post formwork removal, or before concreting. Corrective action involved removing the batten, filling the gap with grout, and re-inspecting. Preventive measures were introduced, such as checklists and inspections to ensure quality compliance and avoid reoccurrence. To conclude, efficient planning, formwork reinforcement, and concreting strategies ensure timely execution. Material management techniques like EOQ, ABC, and HML help optimize resources and reduce costs. Lastly, applying quality control tools enables early detection and correction of errors, helping deliver a reliable and high quality structure. Thank you for your time.